All right, folks. Yesterday or I guess 2 days ago, working on the idea that if we have an ordered pair in the coordinate plane, if I have a point up here that is identified as x comma y, don't care what it is, it's just x comma y. Okay. That if I want to know, because that's rectangular, if I want to know what that location is on the polar graph, how I get to that by traveling at a particular angle. What angle would I have to travel at? And then once I figure out that angle, how far do I need to travel out from the pole at that angle to get to that point, right? Okay. So I'm going to put some things in here that I'm interested in. I want to know what that theta is. I want to know what that r is. And that's all based off of knowing this ordered pair x comma y. Well, if I know that that ordered pair is x comma y, that means I know that distance to be x, and we know that distance to be y, right? Then how do I find r based off of just these two coordinates? Okay, square root of x squared plus y squared. That's the Pythagorean theorem, right? It's a squared plus b squared equals c squared, just redefining a as x, b as y, and c as r. Okay? So our radius turns into that. So now I know how far to travel, but if that's all I gain is, I could travel r that distance, or that distance, or those directions, and all of those are traveling at the same radius here, but none of them get me to the same position as x comma y, right? So I need an angle of rotation that I need to take from the positive x-axis counterclockwise to get there. So that's this theta, right? How do we find that theta since day one? So right now, and use just, because now we got r, so we open the toolbox up a little bit, but the idea is not to use r. So let's assume that so I'm going to use tangent inverse, okay, because I got the opposite side and the hypotenuse, right? So theta will be tangent inverse of the opposite side y divided by the adjacent side x. So that creates the structure for our ordered pair r comma theta now. Okay, and what's nice is we can write some programming for Desmos or GeoGebra that we type in the ordered pair and it automatically creates this stuff for us. We're going to do a little bit of that by hand right now, but that's how you go from. So this is from rectangular to polar. Okay. Is everybody okay with that? All right, so let's reverse it then. And those of you that have dealt with vectors in physics, some of these formulas might make sense to us. Okay. Let's say that I want this point. So I'm in polar coordinates right now, and I've got this point right here identified as r comma theta. R comma theta. So we know that's polar. Which means that I currently have whatever that distance there is, and I have that theta. Okay, those are the things that I know. I want to convert that into rectangular. So if I want to convert into rectangular, I need to know what that distance there is, and I need to know what this distance here is. Is that okay with everybody? All right. Now, if I'm going into rectangular, let's use the same structure, same definition, same variables that rectangular uses. So let's call that y. How could I find, knowing this information here, knowing that this is a known value and this is a known angle, how can I find y? Or what rule or property, function relates these three things together in trigonometry? Sine, right? sine of theta would be y over r, correct? So now what would y be? R sine theta, isn't it? Okay. If you guys remember working with vectors in physics, the formula for your vertical component, a lot of times they call it like b sine theta. So they'll say y equals b sine theta, where all you're doing is trying to find that. It's really just a simple SOHCAHTOA. But in physics, for whatever reason, people struggle with it because it's not presented initially like this, which is something we understand from geometry class, right? If I want to find x, which using maybe physics notation or terminology, this would be the horizontal component, right? Does that make sense? Okay. So the horizontal component, well, that is cosine of theta equals x over r. Remember, I want to use x and theta because those are what are, I want to use r and theta because those are the things that are used right here. Those are defined for me when I have my point. So I multiply both sides by r again. I'll get x equals r cosine theta. Is that okay with everyone? Okay. So that's how you go from polar to rectangular. One thing I should mention, this is going back up to the rectangular to polar. Tangent inverse, what is the output for tangent inverse? What is the restrictions on it? Nope. That's for cosine inverse. Tangent inverse has the same range that the sine inverse has. So this goes from negative 90 to positive 90, or negative pi over 2 to positive pi over 2, which means to us that we're only going to be able to gain results directly from our calculator or from our unit circle that are in those two quadrants, which would mean to us that we wouldn't be able, without a little bit of manipulation, we would not be able to write a second quadrant or third quadrant ordered pair in rectangular coordinates as polar coordinates. Okay, so we need to make sure that we understand that as we go through some of these examples. So the first thing I want to do, and they're kind of backwards in your notes, I want to go down to this section, and just because it's the way that we learned it, we learned going from rectangular to polar first, so that's what I want to kind of concentrate on. So these are all rectangular coordinates, and you understand that, you can visualize that because of the nature of the ordered pair. The nature of the ordered pair doesn't have pi in it. It doesn't have pi in it. Doesn't have the degree symbol, all that kind of stuff. Okay, so it looks like a normal rectangular coordinate. Okay, there can be times where we can kind of maybe be misled and get confused on whether they're supposed to be in polar or supposed to be rectangular when they give it to you. Okay, make sure you read directions. There will always be something, no matter what we're doing, there will always be something that says, take this point that is in polar and convert it to rectangular. Take this point that is in rectangular and convert it to polar. Okay, when they're in polar, there are times, if there's a degree symbol, that's the number one identifier that says this is a polar coordinate. Okay, if there's a pi symbol, I'm going to, it's just an identifier to check the directions and see, does it mean that this point is polar or not. Okay, so always want to be on the lookout for that. Try not to make too many assumptions. So if I want to do 1 radical 3, that is in rectangular form. So what that means to me is we have the point Okay, radical 3 is about like 1.7-ish. So if I'm trying to find that point right there, okay, we can go right 1, up radical 3, no problem. Okay. Now the question is, well, how do I get to that point by traveling at that angle and then using that distance? So if I were standing right here, okay, and I was facing the positive x-axis, the question is, okay, how many degrees or radians do I have to rotate my body so now I'm aligned with this red ray? And then how far do I have to move my body to where I can stop right there on top of that point? Okay? So the way we do that is we're going from rectangular to polar. Okay, you're going to find R. And you're going to find theta. So R ends up being, so if I square 1, I get 1. Square radical 3, I get 3. So R has to be 2, right? And then tangent inverse of radical 3 over 1. Anybody remember what tangent inverse of radical 3 is? It is 60 degrees. Or pi over 3 radians. So now when I write my ordered pair in polar form, it is now the point 2, comma, pi over 3, or 2, comma, 60 degrees. Okay. I like to make those semicolons there. You might see that in some textbooks. It's the notation GeoGebra uses to know that you want to work in polar coordinates. It's just an additional identifier to tell me that the coordinate that is being displayed there is polar and not rectangular. So it eliminates a little bit more confusion. But it doesn't change any structure or calculation or anything like that in the way we interpret the numbers. So what I like to do is just grab real quick my coordinate systems, and it doesn't matter. I mean, these are both scaled right now. You can do these on top of each other. Understand that when we graph something, really what we're doing is that we're graphing on a plane like this, a blank canvas, and then we overlay on top of that blank canvas a tool that allows us to identify those locations. Does that make sense? Okay. So if I lay this tool on top of my blank canvas, or I lay that one on top of it, it doesn't matter. Okay. Because the position, if I look at this one here, we'll do the blue one. If I go 1 square root of 3, okay, you see that it plots them both correctly, right? Okay, would you agree? Okay, so this one here, 1 comma square root of 3, it's about 1 and then 1.7-ish, so that's good. That's the way we interpret how to graph something in the coordinate plane. But look at this one. Would you guys agree that this angle right here that I'm tracing out from the positive x-axis through there, does that angle look like it's probably 60 degrees? Yeah, because this is 90, right? And we've got these 2 extra rays going through there, and they're split up equivalently. So this angle's a third, that's a third, that's a third of 90. So that would be 60 degrees. Is this on the second circle? That makes sense? So that might be one way for us to realize that we do have the same point, okay? But, again, a reminder that it does not matter what template you have, what transparency you have over the top of your blank canvas 2-dimensional plane. If I want to type things in polar coordinates here, I go 2 was my radius, semicolon now, and then I type in pi over 3. it's going to plot right on top of the rectangular coordinate. Does that make sense? And that's how I do. I type it in with rectangular, and then I type it in with polar, and if they plot on top of each other, that's my check. I've done it right. Okay? Desmos is not as easy. Desmos, you actually got to program it a little bit to do that, which, I mean, we can talk about at the end of the period if we have time. But it doesn't have, you know, the semicolon here in an ordered pair. Takes GeoGebra and says, okay, user entered semicolon in ordered pair. Now go to this structure. Go to polar graphing, okay? Or user entered ordered pair with a comma. Go to this structure of rectangular coordinates, and it knows what to do. Desmos doesn't have that built in. Does that kind of make sense on how to do that? Okay, let's jump down here to this one first. This one's pretty easy. Hopefully these we don't have to draw a picture. Hopefully we don't have to run through our formulas. Because this one, because it has a coordinate that is 0, this is a quadrantal angle. Meaning theta is either 0 degrees, 90 degrees, 180, or 270. Or 360, but that's analogous to 0. Okay? So, where is that? Where in the coordinate plane, the Cartesian plane, where is that point? Okay, it's on the y-axis between the third and fourth quadrants, right? So if I'm thinking about rotating from standard position to get to the negative y-axis, how many degrees do you have to rotate? 270. So right there, because your coordinate there for x is 0, you automatically know we're talking about 270 degrees. Okay? Well, let's couple the 0 coupled with the negative y tells me 270. If it was a 0 coupled with a positive y, it'd be 90 degrees, right? Okay? So whenever you see a 0 as the x or as the y, you're either at 0 degrees, 90 degrees, 180, or 270. And then you just got to kind of visualize which one that would be. So theta is going to be 270 here. Okay? How big would be the radius? It'd be 4, right? If I'm standing at 0, 0, and I want to get to 0, negative 4, I need to travel a distance of 4 units. So this is on the fourth circle. So whenever you have an ordered pair that has it's in a rectangular form and it has a 0 as one of your coordinates, the other coordinate's absolute value is your radius. Okay? So 4 is my radius. And then you have to decide what angle, what quadrant, or quadrantal angle we are using for theta. That kind of make sense? So if I go, let's give you another one here real quick. Let's go 3, 0. So what would be the radius? Be 3, right? Think about this. 3, 0 is going to be right there, correct? Well, how do I go from 0, 0 to there? What's that radius I need to go out to? It'd be that one. Okay? It's going to be that number right there. 0 is going to be how many degrees in? So I'm going to go to 3, 0. 3 zeros on this x-axis. So how many degrees do I need to go to rotate from here to get there? 0 degrees, right? That makes sense? Okay. Now this is an x, y. This is an r, theta. Okay. If you want to go 360, that would be fine, or 2 pi, that would also be fine. What if I want to go negative 3, 0? What if I look at that? What would my radius be? Still be 3. Okay. But now negative 3, 0 is going to be over here, correct? How many degrees do I need to rotate to get there? 180. Okay, so hopefully those kind of circumvent, or quadrantal points circumvent you having to do the formulas to find r and to find theta. Let's do, yes? Let's do this one. Okay, so we're at negative 2, 2. If I want to go into polar, I'm going to take R, and it's going to turn into negative 2 squared before, 2 squared before, so that's going to be 8, radical 8. You can simplify that if you want. I'm just going to leave it as radical 8 right now. If you want to go 2 radical 2, that's fine. Theta, though, is going to be tangent inverse of my y value divided by my x value. So it's tangent inverse of negative 1. What will my calculator spit back to me for my tangent inverse of negative 1? Say again? Negative 45. Good. Because remember, theta is between those two things there, right? So this is only quadrant 1 and quadrant 4. Where are we in the rectangular system here? Quadrant 2. So there's a problem here. If I'm looking at the polar coordinates, and I use exactly what my calculator spits back, and I don't use any trigonometric logic, okay, the polar information just provided said that you're going to travel at negative 45 degrees, and you're going to travel out radical 8 units. And that's the wrong point. It's not this one, right? Okay. How do I get this point here transitioned to up here? Say it again. Add pi or 180 to that, right? And the reason we do that is because if I take, so if this is my terminating ray, and I want to get to this one, okay, I can take the opposite ray, and that's going to make that angle right there the same as that one because they're vertical, right? It's going to make that 45 degrees. So then the theta that we want from standard position would be that one, which would be 135, right? Which the 135 can be realized by taking negative 45 plus 180. Okay? So the real theta that we're interested in here is 135 degrees. So we get radical 8, comma, 135. Okay? Generally, that's the best answer for the mere fact that theta is between 0 and 360, as well as r being positive. If I graph negative 2, 2, we want that point there. If I were to graph square root of 8, negative 45. So here's the thing with GeoGebra. Negative 45, it doesn't know, it kind of looks like it's the right spot here, but what that's doing is negative 45 radians. So it's traveling clockwise, negative 45 radians, until I put the degree symbol on there. And you see how it kind of moved a little bit? Oops. There we go. So we wanted negative 2, 2. So those 2 points, okay, this is the one that was in rectangular. This is the one that we get directly from our formulas for polar. If we look at the polar graph here, are those on opposite rays? And what I mean by determining are they on opposite rays is, can I connect them with a point with a line? That line goes to the pole, right? So this one is on the opposite ray as that one. Okay, B is the one that we want to locate. So if I'm at A, like Jim had told us, we could rotate 180 degrees. We could add 180 to it, and it gets us there. Could I also subtract 180? Would that work? Could I say negative 225? That's fine. That'll work. Okay. There's another thing that I can do. You guys remember what we do with the radius? If I'm taking point A and plotted point A, what can I do with the radius to get A actually to transition back onto the opposite ray? Make it negative. So if I take A and make the radius negative right here, and then hit apply, you see that put A on top of B, right? Does that make sense? So there's a couple different ways that you can do this. I want to go negative radical 8, comma, negative 45 degrees, that's fine. Okay? And then obviously in either one of those, then you can start adding 360 or subtracting 360 from theta to get additional solutions or structures for the ordered pairs that provide the same location. Is that okay? This is just the one thing we need to understand. This is a problematic thing for a lot of students, is that they think when I run through the formulas that it gives you exactly what you need. If this point starts in the second or third quadrant, you got to do a little bit extra with the theta. Why don't you guys real quick do this one? Let's go -4, comma, -5. See if you can put that into polar coordinates for me. Should I see R to be radical 41? Okay, when you find theta initially, 51.34 degrees, approximately. If you're in radians, you get 0.896. Okay, so, but is that, if I go 51.34 degrees, is that in the third quadrant like that point there is? No. So what do I have to do to this number? Add 180 to it. Okay. So plus 180. 231.34 degrees. So our ordered pair in degrees will be radical 41 as R, and then 231.34 degrees as theta. Okay, and that's obviously in degrees. If we're doing this in radians, and I like to show this intentionally, because if we're in radians, it gives us, so I add pi to this, it gives me 4.037. I should probably round that to an 8. So give me that. Does this look a lot like an ordered pair from the rectangular system? That makes sense? Because I didn't put any units on here, because in radians, they're a dimensional unit anyways, or dimensionless unit anyways. That looks very XY-ish, okay? So that is why maybe adding a semicolon here instead of a comma might create that differentiating feature to tell me, hey, this is polar, okay? And that would be something that I would do on my own, in my notes, in my work, just so that I keep things straight, okay? Or I think what GeoGebra will do if we're in radians, it will actually add that unit here, it'll say RAD at the end. But a lot of times textbooks will just show you that with a comma, and you just gotta know that it's in polar per the context of the problem. Is that okay with everybody? So let's go up here to these, and let's do B first. So B, so this is polar. The directions say it, but another thing that I look at this that looks very XY-ish, and I can plot. Think about this. If you are in the rectangular system, you can go over to the right 2 units. You can go up pi over 3 units. So you can plot. I don't know why I didn't keep them in there. Oh, I do know why. All right, so you can go over 2 units, and you can go up pi over 3 units, and it will give me that position right there. Does that make sense? Okay. So this can be viewed as rectangular. But when I see that pi, I'm always going to glance real quick at the directions. It says convert a point from polar to rectangular. So I know this is polar then. So I know that that's a theta and that's an r. Does that make sense? I'm really I'm trying to reinforce that idea because I know people in the past have really just mangled homework assignments and tests and quizzes because of that lack of understanding there. That's an r comma theta. All right, so if I want to change this to x and y, this is really easy. X, through our formulas in the analysis that we did at the beginning of the class with that triangle, x is always r cosine theta, and y is always equal to r sine of theta. X and cosine go together. Okay, if you forget y, you can realize that x and y are alphabetical respectively. Cosine and sine are alphabetical respectively, so x goes with cosine, y goes with sine. Okay. My hope is that we know mathematically why that's true. But now all we got to do is say, okay, well, the x-coordinate is equal to 2 times the cosine of pi over 3, and the y-coordinate is 2 sine of pi over 3. So what is pi over 3? What is cosine of pi over 3? From the unit circle, be 1/2, right? So we got 2 times a half. Obviously that equals 1. What's the sine of pi over 3? Radical 3 over 2. So then the y value is radical 3. So I get the point. X was 1. Y was radical 3. That's exactly what we did down here. We started with 1 radical 3, and we came up with 2 comma pi over 3, right? So start with 2 comma pi over 3 should inherently get back to 1 comma radical 3. But that's the way that we go back into rectangular coordinates if we started in polar. So that's our x and that's our y. Okay? Using Desmos real quick. I showed last class, so I think maybe I'll show you guys this as well. It's not as easy. So you got to understand how Desmos operates. If I start trying to define letters as or components to equations with using r, so I say like r equals 3, okay? In polar equations, and I'm going to show you this tomorrow, x squared plus y squared equals 9, which is the equation of that circle in rectangular form. is r equals 3 in polar form. Okay, r equals 3 is a very simple formula, which allows us to do some algebra later on a little bit more conveniently than x squared plus y squared equals 9 does. But if I start defining things using this structure, or Desmos is going to have issues with me, okay? So what I want to do is I want to eventually figure out, okay, if they give me r comma theta, okay, r comma theta, okay, then how can I take that information and convert it into rectangular form, okay? Well, I'm going to have to use, just because I don't want to use r, I'm going to have to use r, and I'm going to put a subscript of 1 there. Don't worry about the slider yet. But if I have r comma theta, think about what we just did. We said the x value was r times the cosine of theta. And the y value was r times the sine of theta, correct? Okay. Now, if I want to figure out what r is, let's say r, and our problem was 2, right? Okay. Now, there's some janky stuff going on over here because of the way I've defined these things right now. So just be patient with me. And theta we said was what, pi over 3? Okay. Now none of this stuff is working the way I want it to yet. But it's not. I mean, I guess it does transform those because I have now established what r is as an integer, and it's not trying to pull it out of a. It's not trying to use that circle idea. It shows me now the intersection right here, okay, of the point that we're looking for. Does that make sense? Okay. Now, if you want to do it that way, that's fine. That shows you the intersection of those two lines. I don't know if I can go x comma y, if it will plot those for me. It doesn't. So I go f comma x comma y. Nope. So if I want the ordered pair to be plotted, there's a couple different ways I can do this. I could say, maybe I'll call that A and call that B, then come down here and graph A comma B. And I don't want this to be plotted anymore. Okay, I don't even need that anymore. So now we've designed in Desmos exactly what is behind the scenes in GeoGebra when we type in an R value and a theta value. Does that make sense? GeoGebra captures those, runs them through these two formulas, takes that as your x value, takes that as your y value, and then plots them against each other, and it gives you the rectangular coordinate. Does that make sense? Okay. And you can then obviously, if it's a move that you can see that's moving along that radius at pi over 3. You can change your theta. This theta can become, if I go and change that from like pi over 6 to pi over 3 to pi over 2, keeping the same radius, you could see it going around that circle of that radius. But that's how we can maybe get Desmos to operate for us with transforming polar into rectangular. And we could reverse engineer it to do rectangular into polar if we wanted to. Okay. Is that okay? That should get you through a bulk of 8.1, okay, in WebAssign. Tomorrow, I know we're going to have about 10, 15 minutes in class tomorrow, but I want to take like an equation like 3x plus y equals 7 that is in Cartesian coordinates, and I want to transfer it to a polar equation, okay? So we'll do a little bit of that tomorrow. Do maybe 1 or 2 examples of that, and that should allow you to then finish 8.1.